Hello, my dear students, and welcome to the first official lecture for the Semiconductor Devices module. As I mentioned in lecture number 0, in this lecture, we are going to flash back the main important part we have already learned in your material course 2 semesters from now, which will be as a prerequisite for our current Semiconductor Devices module. So I believe that all slides that you are going to see in this presentation, you already have learned it before in your material course. However, we just refresh your memory before starting our semiconductor devices course, starting with chapter 2 or lecture 2, dealing with the PN junction. Let's start now our revision lecture. Okay, so as I'm titling this presentation or this lecture with semiconductor material, so the first question that can come into our mind is, what is the difference, or what are the different classifications for material? So as we are dealing with electrical semiconductor devices, so we will be more focused toward the classification of the material based on the electrical properties. And the main electrical property is the electrical conductivity, or what's abbreviated by sigma. Now the question is, how could we measure sigma? How could we measure the electrical conductivity in a lab? Actually, the experiment is very easy. So assume that you have a bar of any type of a material, unknown material. You don't know what is the material. So what you are going to do is simply that you are going to pick up a variable DC supply and an emitter. And you are going to connect the material with the variable DC supply while considering the emitter in a series connection, as you already know from your previous measurement at the electronic courses. Then you start to change the voltage and read or detect or observe the current. In this case, you are validating what's called the Ohm's law. Delta V, or the different potential, different in potential, equals to the current times the resistance. As far as you have the V and the I, then you can calculate R, or the resistance. But please don't forget that resistance is a material as well as a dimension property, because resistance equals to rho times L over A. So length is affecting on resistance. Cross-sectional area of the bar is also considered in the resistance. However, the resistivity, or rho, is a pure material parameter. What I mean is simply if you have two copper wire, one is 1 meter long and the second is 5 meter long, then based on this relation, the resistance of the 5 meter long copper wire will be greater than the resistance of the 1 meter long copper wire. However, both have the same resistivity. This is typically the difference between the term resistance, R, and the term resistivity, or rho. So knowing the resistance from Ohm's law and knowing the dimension, specifically the length and the cross-sectional area, you can determine the resistivity, or rho. And as you already know that sigma, or the conductivity, equals the reciprocal, or 1 over rho, you can calculate sigma in terms of rho. Herein, if you pick different types of material, a collection, randomly collected set of material, and you build this experiment over all the materials, you will get 3 sets of results. The first set with a relatively high sigma conductivity. What I mean by relatively high is in the terms of 10 power 4, power 5, power 3, power 7, power 8, something like that. And you will have another set of relatively or extremely low sigma, 10 to the power -15, -14, something like that. And you have a family in between. not that high like the first one, and not that low like the second. Accordingly, you can classify your materials based on the conductivity. So we will have a group which has a high conductivity, and what we will call them conductors. And we will have another group with an extremely low conductivity, and we will call them dielectrical material or insulators, or non-conducting, of course. And we will have the in-between group we will call a semiconductor. So by this learning by doing experiment, you can classify the materials into these three groups. But the question will come is, why conductors are conductors? I mean, what is the property inside the copper that makes copper a good conductor? And on the other hand, what is the property inside the glass which turns glass to be a non-conductor? This is our next approach. So let's start with the conductors, for example, copper. And before considering the question why copper is a conductor, let's first ask another question. What is conductivity? As you know from definition, a conducting material is a material that transfers electrical current. And electrical current basically is dq by dt, or the rate of a change of a charge. So whenever you have more and more and more charge, your conducting capability increases. So basically, the conductivity is directly proportional to the charge. But my dear students, this definition is wrong. Conductivity is directly proportional to free charge, not any charge. Because any material has electrons rotating around the nucleus in their atoms. So basically, every and each material has a charge, but not every and each material has a free charge. What is the definition of free charge? A free charge is an electron that is too far from the nucleus so that the attraction force, or between quotation, the bond between the nucleus and the electron, can be broken. So, for example, if we collect this single atom of copper, you can see that the single atom of copper includes different orbits, and each orbit contains a number of electrons, of course. Basically, as much as you go for a higher energy level, I mean the distance between the electron and the nucleus increase, the weaker the attraction force. So whenever I think to pick up a free electron, logically speaking, I should think about this last electron, the electron in the outermost energy level, or what we call the valency level, because this is the easiest bond to be broken. However, if I consider to break the bond for this electron, which is in the inner shell of the nucleus, which is very difficult. Basically, it's impossible to break such a bond. It's highly connected to the nucleus. So the probability to have a free electron is related to those electron exists in the outermost energy level. However, there is another factor affecting them, which is the nature of the bond. What I mean by the nature of the bond, as we learn from the chemistry classes, that each energy level acts to be in a steady state. And what do we mean by steady state is either to be totally filled, completed, or to be totally empty. So in order to make an energy level saturated or in steady state, you can either fill in the energy level till it reaches its maximum, like the one here, for example, this one. So for example, the maximum of this one, 16 or whatever, then we have 16 electrons in the outer in this energy level. That's why this energy level is saturated, or to have 0 electrons. Now, if I tell you that this outermost energy level for copper, for example, needs, for example, 8 electrons to be saturated. Currently, it includes only 1. So, in order to reach a steady state, you have 2 options. Either to gain 7 more electrons, so that this energy level becomes with 8 electrons unsaturated, or to kick out this electron to become an empty level. Of course, it is easier for the atom to kick out 1 electron rather than to gain 7. Accordingly, you can expect that the bond between this electron and the nucleus is too weak. Electron is acting to get rid out of this electron atom. Sorry, is acting to get rid out of this electron from the atom. So you can easily break the bond. You have to pay nothing to break the bond. But what if you have another material with 7 electrons in the outermost energy level? Herein, we have 7 electrons in the outermost energy level, but the bond here is very strong because, logically speaking, this atom will act to gain 1 electron rather than to get rid, to kick out 7 electrons. So this will be an insulator. On the other hand, we can have something like that. A material with 4 electrons in the outermost energy level. This is an in-between. It's a trade-off scenario because you can either lose 4 or gain 4, equally weighted. So you are equidistant between being a conductor or between being an insulator. That's why we call this as a semiconductor material. So now you can address the question, why copper is a conducting material? Because each atom of copper can donate with 1 free electron. The question is, do we have such a huge conductivity due to only 1 electron? The answer is yes, because basically in each 1 mole of the material, you have an Avogadro's number of atoms. I mean something like 10 power 23 atoms per 1 mole. So if each atom donates 1 electron, so per mole, you will have something like 10 to the power 22 or 23 electrons. That's why copper has such a huge conductivity. However, whenever you go to glass or chloride, for example, here or whenever, you don't have any free electrons. That's why it's an insulator. But for semiconductors, it might be, or it might have some free electrons, but under certain conditions. This is what we are going to illustrate in this lecture. But before going to this concept, let's also show you something that semiconductors, which is of course our material of interest in this lecture, are those materials located in the 4th group in the periodic table. So they have 4 electrons in the outermost energy level. These are the atomic structures. I believe we already tackled in more depth this point in your material course. But now let's turn to another view, which is for our study more important. In this example, we are dealing with what's called an isolated atom format. This is most probably the way where people from chemical background, chemistry background, deal with atoms or with materials in an isolated atom format. But in a realistic case, material include billions of billions of billions of atoms. It's not only 1 electron, 1 atom. We have a huge number of atoms. So this silicon atom have a set of, or has a set of neighbors, and they are close together to each other, and they are forming silicon. So what the neighbors affect, or how the neighbors can affect such energy level. Let's see this important, and let me say this very important video. Okay, let's do it. Okay, so as you can see here, this is the nucleus for a silicon, and this is the atomic distribution of silicon. We have an inner energy level with 2 electrons. Then we have another energy level with 8 electrons. If you remember from chemistry, this is called LNM, and the K element, and this have a 4 electron. So this is saturated energy level. This is a saturated energy level, and this is a partially full. It includes 4 atoms, but it can accept another 4. This is typically how silicon atom looks like. Then this silicon atom have another neighbor, a second, the first neighbor. The first neighbor of the silicon atom has its own energy level. That's why we have now what's called an overlapped energy level. As you can see, each 2 energy level with the same energy are overlapped together. So we have here 2 energy levels, each with 2 electrons, 2 energy levels, each with 8, and 2 energy levels, each with 4. Then let's do the next. We have a third neighbor, and this third neighbor will have also its energy levels. And again, this energy level will overlap together. Okay, so and so on till we form this structure. This structure is what we call, my dear students, an energy band. So an energy band is a set of energy levels overlap together due to the huge overlapping of the atoms. We have billions of atoms, billions of atoms. That's why we have such an energy band. Okay, so I can go somehow faster. Okay, let's start from here. Okay, perfect. So as I mentioned, these 2 levels are called a core level. Why we call them a core level? For 2 reasons, actually. The first, because they are too close to the nucleus. So they are, or the atoms in these energy levels are extremely strong bound to the nucleus. The second is that they are saturated energy levels. So I can do nothing with such energy level. So that's why we call this a core energy level, as you can see. Now this is the valency level, and that's why this is a valency electron. They are the valency because this is the outermost energy level that includes electron, because you have higher energy levels, but these high energy levels are empty. So this is the outermost partially filled energy level, which is the valency level. And these, of course, are the valency electrons. They are bounded to the nucleus, of course, but with a weaker energy because they are far from the nucleus. This is the valency electrons. And that's what we call the conduction level. Why we call this energy level as a conduction level? This is simply because this energy level includes or if electrons transfer from this energy level to the next one, then it becomes more and more far to the nucleus, and that's why we can consider this as a partially free electron, because it's now more and more far from the nucleus. So let's transfer these concepts into a band. Whenever we have neighbors, whenever we have more and more neighbors, these energy levels, as you see before, will be turned to be energy bands. So let's go to the energy bands, this figure. So applying the same concept, my dear student, we will find that this first energy band is a core band and it's fully occupied. Same for this one, as you will see. This also is a fully saturated energy band, and also it's occupied. I'm sorry, let me return back. Okay, that's perfect. Okay, okay. So the first two energy levels are fully occupied, and they are very near to the nucleus. I don't need this energy band. But this energy band, the third one, first, it's relatively far from the nucleus. So the energy bond is weaker. Second, it's partially full. So it's a level of interest, or it's a band of interest. And this is the target band. I'm targeting to have more and more free electrons to convert the semiconductor into a conducting material. That's why I am targeting to transfer or to move this electron from the third energy band, which we will call it the valency band, to the upper energy band, which is the conduction band. So from this step and later on, we are going to focus on this area. Let me make it in a better color. Let me make it red, for example. Okay, I think this will be better for you to see. Yeah, so we are focusing on this area, this rectangular area. This is the valency level. I will again open my laser pointer. Okay, perfect. So this, okay, this is the valency band. The region between the valency band and the conduction band is called the energy gap, and this is the conduction band. So what we are targeting is to move these electrons from the valency band to the conduction band, so we have more and more free electrons, and then this semiconductor turns to be a conducting material. This is basically the main conditions we are seeking for in order to have or to turn a semiconductor to be a conductor. Accordingly, we will have what's called an energy band gap. An energy band gap is a diagram. Oh, sorry, an energy band diagram. I'm sorry. An energy band diagram is a diagram that represents the valency band, which is the pink area on the bottom of this graph, the conduction band, which is the blue area on the top, and what is in between in the energy gap. So in order to make, or in order to move a single electron from the valency band to the conduction band, you have to give this material or this atom or electron an energy equals to or greater than the energy band gap. So this material, this electron can jump from the valency band to the conduction. This is typically what's the condition needed for a semiconductor to have some conducting capabilities. The higher the energy you give to the material, more and more electrons will jump from the valency band to the conduction. So this is typically the energy band diagram for a semiconductor material. If you would like to have a similar diagram for an insulator, it will look like this. It's again have a valency band and conduction band, but the energy gap is extremely huge, so that whatever energy you will give, electrons will not be able to jump from the valency band to the conduction band. So you will never have a free electrons or a conducting capabilities for an insulator. However, for the conductors, still you have a valency band and the conduction band, but the valency band and the conduction band are overlapped, so you don't need to do effort. Automatically, electron will move from the valency band to the conduction band, and automatically you will have electrons free. This is typically copper. You don't need to do any effort to make copper conductor. It's conductor by default. Electrons can move easily from the valency band to the conduction band. This is typically the properties for a conducting material. Okay, perfect. Let's turn to another important definition. Again, this is the valency band, but now the valency band is green, and now the conduction band is red. We have energy gap, which is the distance between the valency band and the conduction band. We have a set of electrons staying in the valency band. But the question is, we need energy, as I just mentioned, in order to turn this material to be a conducting material. You should give some energy to these electrons so that they can jump from the valency band to the conduction band, and then you have a free electron. So we need energy. By the way, the material in this format is an insulator, basically because you have no electrons in the conduction band. So what type of energy we need? First, we have to agree that this energy should be greater than or equal the Eg, which is the energy band gap. Then, from where or what type of energy we have? Before searching for external sources of energy, let's start thinking about the internal sources of energy. What I mean by internal sources of energy is basically any material has internally its internal thermal energy, which is defined by 3/2 kT, where K is Boltzmann constant and T is temperature. So if this 3/2 kT, where T is a temperature in Kelvin, by the way, so at room temperature T is equals to 300 and K is a constant. So you have some sort of energy by the room temperature. If this energy is equals to or greater than the Eg, then naturally, due to the internal thermal energy of the material, some electrons will leave the valency band and will turn or will transfer to the conduction band. And then you will have some naturally free electrons in the in the conduction band for any semiconductor. Accordingly, at room temperature, the conductivity of the semiconductor is not very low. And let's now return back to this slide. Here, you can see it here. At room temperature, when we go together in the lab and measure this sigma, we get some sigma. Of course, it's not as equal as metals, but it's not as low as insulators. This is basically because due to the internal thermal energy of the material, some few amount of electrons can transfer from the valence band to the conduction band. And that's why we have relatively high conductivity, of course, with respect to insulators. So this is the case for a semiconductor. And we will call these electrons who are in the conduction band by nature due to the internal thermal energy at room temperature, we will call them what's called the intrinsic concentration, if you remember this name, or what's called the Ni. For example, Ni for silicon at room temperature is 10 × 10 centimeter per minus 3. That means by room temperature, without any external sources of energy, you can find 10 × 10 electron in silicon per centimeter cube. One of you may ask here a very important question. Is 10 × 10 is a low number? It's very huge. It's 10 billion electrons per centimeter cube. This is very high. So why silicon is not a good conductor? The answer is in copper. If you remember, I told you that for a copper atom, each atom donates with 1 electron. And per centimeter cube, you have nearly something like 10 × 23 atoms. So in copper, you have 10 × 23 free electrons per centimeter cube. However, in silicon, you only have 10 × 10, which is 13 order of magnitude lower than copper. That's why silicon is a semiconductor, not a conductor. Finally, to terminate this slide, we have to remind ourselves with a very important definition, which is a hole. A hole is a broken bond. So before the electron to gain energy and to leave the valency band, there was a bond between this electron and the nucleus. Now, due to the internal thermal energy of the temperatures, the internal thermal energy inside the material, this energy will be or is capable to break the bond. So electron transfer to the to the conduction band and leaving an empty space in the valency band, which we call it a hole. However, never say that hole is an empty space, because hole is a broken bond, not an empty space. Why am I mentioning this? Because if I told you in this format, do we have holes in the conduction band? So if you consider holes that are those empty spaces, your answer will be typically yes. We have a huge number of empty spaces in the conduction band. However, in the conduction band, you have zero holes because you don't have any broken bond. But now, when the electron transfer from the valency band to the conduction band, you now have a created hole or a generated hole in the valency band, which is a broken bond. So, as a general definition, holes can exist only in the valency band, and free electrons can exist only in the conduction band. This is typically the case of free electrons and free holes. Now, in the next part, my dear students, we are going to investigate some phenomena about how we can calculate the number of electrons in the conduction band or the number of holes in the valency band, which should be typically equal if the material is what's called an intrinsic material. Otherwise, we will transfer to what's called an extrinsic material, where there is a doping effect. This is the termination for part number 1, and see you later on with part number 2, lecture number 1, semiconductor materials. Thank you very much.